So this is the, I don't know, parallel lab thingy. It's page, I think it's page 13. You have to build these two circuits and analyze them, and we're going to talk about how the capacitor affects each circuit. So for this first one, right, it asks you, when you first connect it, what is the brightnesses of these light bulbs, and I drew them as resistors. What are the brightnesses going to be? And after a long time, what will the brightnesses look like? So you see these three resistors in parallel, but one of them has a capacitor in front of it. And what we remembered, or hopefully what you can kind of remember from red marker, from the last lab, was that when you had a circuit like this, right, and a resistor and a capacitor, initially this light bulb or whatever resistor won't consume any current or any voltage or any power. No current will go through it because all the current initially will go through this capacitor. It acts like a wire, right, initially. So you might be tempted to say, okay, well, all the current's going to go through this top branch because there's a capacitor. It's less resistance. But there's a resistor right after it. So if we were, right, a capacitor basically acts like a wire. You can just, like, to visualize, you can literally just draw a wire, right? And that's your circuit to begin with, at least for that first instant. So yeah, all three are gonna have the same brightnesses, right? Because they each get, they're equal resistance, so they're each gonna have the same current, and they have the same voltage, so they're gonna have the same power consumed, same brightness. Now after a long time, what's gonna happen is after a long time, that capacitor is going to get charged. So what you have to kind of think about is this idea of loop rule. So we know not by loop rule, but really by parallel branch rules. Each branch is going to have the same change in V. So change in V. It's going to be the same change in V. Maybe it's like 9 volts. It's whatever the voltage of the battery is. So we could say it's 10 volts. Each branch is going to have that 10 volts going through it by our parallel rules. So initially, before the capacitor was charged, it started off with 0 volts, right? There's no charge on it. There's no potential difference. All of the 10 volts would be going to the resistor, right? As current passes through it, that's going to have like a 10 volt potential drop, right? But as the capacitor gets charged, right, if you think about the voltage, right, so change in V is going to equal, so for this branch, the change in V is going to equal the battery, so 10 volts, which is going to equal the capacitor voltage plus the voltage drop the voltage consumed by this resistor, IR. So over time, this number, right, V capacitor, that's going to get bigger. So what's going to happen to the voltage drop? It's going to get smaller. Well, the only way it's going to get smaller is if the current gets smaller, right? You can't change R. The current going through the whole capacitor is decreasing. Eventually, this hits 10 volts, right? So once this hits 10 volts, there's going to be no more current going through this resistor. So over time, this top bulb will dim down, and it'll basically become 0. So what's going to happen to the other two? Well, once this capacitor gets charged and no more current goes through this, you can kind of just ignore that part of the circuit, right? Just like how we could ignore the capacitor initially and draw it in as a wire. Now we can ignore that whole part. It's just these two in parallel. Well, by parallel rules for resistors, we know that the equivalent resistance, 1 over R, 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So what actually ends up happening is when you get rid of a resistor, right, you're getting rid of this term. So this reciprocal 1 over R gets smaller, right? Because I'm adding like less of these, like 1 over R, right? It's now 2 instead of 3. So this fraction gets smaller, but it's the reciprocal. So if 1 over R gets smaller, because it's a reciprocal, R itself gets bigger. You get more resistance. Less resistors in parallel means more equivalent resistance. So more equivalent resistance means there's going to be less current. So as this thing kind of not dies out, but gets no current, you can ignore that part. Well, now your equivalent resistance is bigger, current is less, so these two will actually shine less because they're getting less current once the capacitor is fully charged. So yeah, I think that was kind of like the majority of the concepts. I think, predict what will happen to the current reading, right? I just explained it, it'll get smaller. What will the voltage reading be of this capacitor? It's going to be whatever the voltage of the battery is, right? 10 volts, 9 volts, whatever. Because this branch is going to receive 10 volts, and like I showed, it's eventually going to hit 10 volts. Cool. Now let's take a look at this little resistor thing, or circuit, sorry. For this circuit, we have kind of a series and parallel mix. Same idea, we have resistor, 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 and then a capacitor in front of it. So we're going to see like what happens. So I think, what was the question asked? As the capacitor charges, what happens to the brightness of L1? Okay. Wait, I'm sorry, I'm reading my answer. I'm so tired today. What's going to happen to the brightnesses initially? Well, if this is L1, this is L2, and this is L3. Remember, the capacitor initially when the battery is just on is just a wire. You can treat it as a wire. Like you can draw like in your head like a wire going through that thing because it's basically acting like a zero resistance wire. It's not going to affect the circuit. I guess you'd say it's not going to affect this circuit initially. So it's going to be L1 has a greater brightness than L2, which would be equal to L3. So why? L1 is getting the most current, but then this current's going to split, and they'll get it both equally because they have the same resistance. So by Ohm's law, they'll get the same current, but it'll be less than L1. Sorry about that. Over time, what's going to happen to the brightnesses? Well, over time, what's going to happen is this capacitor gets charged. So more charge, right? Going back to this thing, it's going to equal. So this time it's not going to equal the voltage of the battery, but it's going to equal, and the reason it's not going to equal the voltage of the battery is because now we're also in series. So this resistor is going to consume some of the voltage, so it's not going to be exactly voltage of the battery. But it's going to be the voltage of like, I don't know, whatever, right? It's going to be some same voltage. So as your capacitor gets bigger, this voltage stays the same. So the resistance or the current goes down. And once it reaches that max voltage, whatever it is, this light bulb is going to be 0, L2. So now once this gets fully charged, remember, you can just ignore that part of the circuit, and now we have two in series, right? When you can ignore it, we have two resistors in series. They're both going to have the same brightness, so we can rank the brightnesses. L1 equals L3 is greater than L2, which is 0 brightness. So, well, will they shine? So after it's fully charged, will they shine brighter or dimmer? They're going to shine dimmer. They're going to shine dimmer because remember, when you remove a parallel resistor, you're increasing the equivalent resistance, less current's flowing through the circuit, and these two will be shining less bright. So hopefully that makes sense. And the meter, right? So the meter readings, the current's going to get less throughout the circuit, but this voltage of the capacitor will get more until it hits some kind of max voltage, whatever that is. You would need to know the actual values to be like, okay, well, this is 20 volts, this is that much resistance, and you can maybe figure it out. But yeah, that's the slab. So hopefully this makes sense. Thank you for watching. Have a good one.